So we are again in the, let's say, paradigm of our VerityOps project, where we take as an input to our process cybersecurity requirements. Many times they are expressed in natural language. Natural language is the most commonly used technique currently for specifying requirements and cybersecurity requirements. So what we want is we want to actually try out and exploit like modern and NLP technologies based on machine learning to first extract security requirements, so to understand what is security in the requirements list, classify the security requirements, maybe identify entity properties, apply specific formal patterns with the goal to find out specific tests and specific recommendations how to address those security requirements. So in the end, so we get at the entry cybersecurity requirement specification as a document, and at the end we should obtain some concrete recommendations, concrete tasks to address those security requirements, or at least help developers to address that. Why this important? What's what we call actually security requirements. So security requirements is a kind of statement, let's say, natural language, that specifies some security property that needs to be achieved, any assets to be protected, or protects out from specific threat. And this cybersecurity requirement is usually fulfilled by specific countermeasures or specific cybersecurity mechanisms that is deployed or kind of developed within the system, or by kind of protecting measures like that ensure some security constraints, restrictions, assurance, like permission, compliance, and all of that security requirements can actually specify. To give you an example, I have here a document by NIST, right, that presents an example by NIST about security quantification for a specific system called distributed manufacturing data. And it's a typical document. We can actually look inside of those requirements. And if you look to non-functional requirements here, we will see that security requirements are here specified in a really brief way, right? So like security software system defined and series must follow industry recommended practices for secure software development, and at least it should fulfill the practice in principle of least privilege, right? So what we see commonly, it's quite common in industry to have the security requirement application quite vague and generic. Also, it should be noticed that in this document, I mean, if I was like a security specialist and I wanted to know about security, I would like definitely go first and check this one. But it's not everything about cybersecurity in this document, as we can discover, and we discover that later. So some cybersecurity could be spread out in this document. For example, here one can notice that like maximum person time required to fix security defect must not exceed 2 person days, for example, which is kind of called maintainability, but it also relates to cybersecurity. And if I were somebody who is interested, like to check and verify how secure is my system and what should I do, I would need manually parse this document and read it really carefully, looking at all the sentences. And it's actually the process that would be error prone. Let's say human can mistakenly interpret that. Actually, our idea here is to use some NLP methods to define and detect what is related to security in this document. And I will show you a few techniques in doing that. So, but before that, let's just discuss a bit about NLP in general and NLP for cybersecurity, like those requirements engineering. Right. So, so what kind of NLP methods used in requirements engineering? So first of all, there is classification like binary. Is it security or not security related? So it's for predicting specific categorical classes. It could be extraction, retrieving some specific information like single or multi-word terms. Who is the object, who is subject, and so what are the constraints? So it could be based on glossaries, on a specific domain documents. It could be clustering. So, for example, if I want to organize documents and some kind of cohesive subset. So, for example, I would like to cluster my requirements and those related to authentication, those related to integrity. So to treat them in the groups, all right? Also, we can use NLP for what we call detection. So trying to figure out what are the ambiguities in the requirements, so detect some unclear requirements that should be corrected and should be more precise, let's say. So we can detect different lexical issues, vague phrases, weak verbs, syntactical ambiguities. Also, if the requirement follows a predefined template or not, recognize also equivalent requirement. There is a body of research on equivalent requirements as well. So, in addition, NLP methods are used in code. Trying to detect vulnerabilities in the software components by NLP methods, right? So analyzing syntactical structures of the code, right? Also repairs. So sometimes we can transform a vulnerable code into non-vulnerable code. There are studies like this. So if you want to see some of those, please look at our chapter. There could be also some specification analysis, like trying to understand what are the security risks in product before the code is even written. So applying some expert method for automatically processing vulnerability descriptions or product specification. So assess the riskiness of this particular project. And so this is a bit of group of various, let's say, major methods, NLP techniques, let's say, applications in requirements engineering. So we actually have quite a long list of that in our chapter. What should we also remind how the performance of those NLP methods are evaluated. So we have most of the studies like use precision, recall, F1 score metric. So precision is, let's say, if we try to detect what is security, what is not security, what is requirement, what is not requirement. So if we can correctly identify specific class, well, this one is, this sentence is a requirement, or this sentence is related to security. So if we correctly identify that, it corresponds to ground truth. So then we count that as kind of precision. So high precision means, so in all the, let's say, sentences that we identified as requirements or as included in the class, they're truly included in the class. And recall typically says how much of the entities of specific class we actually touched. So, for example, if we have low recall in our classification task, it would actually mean that we missed tons of requirements. We haven't actually processed them properly. So it's very important to have high precision and high recall in these classification tasks. And F1 is some kind of harmonic mean between precision and recall that shows, let's say, average of precision and recall. And it's very much in use in this classification task performance evaluation. So, and like later we actually discuss our results based on this performance metric. Right. So deep learning, actually deep learning made quite a revolution starting from 2018 with the appearance of the transfer learning methods, bidirectional encoders. And it is a consecutive transformation of various representations of let's say, tokens in more abstract level. So we create specific vectors out of words or sentences, right? And we compare those vectors and try to predict if they, let's say, belong to a specific class, right? And as soon as these methods appeared, very soon they were used in requirements classification tasks, and so Winker, DECTR, and others use actually quite various methods for classification. Some, like Winker, obtained 80% of performance, let's say, with using his particular methods. DECTR with using word-to-vec and CNN, 91% of F1 score, which is actually quite promising result. In transfer learning, an appearance of these transfer learnings that are trained on huge data sets that capture concepts, so meanings of natural language text, they showed actually quite outstanding performance in various NLP tasks. And many researchers actually used those particular methods to classify requirements. And one important thing to underline with this method that typically when this model exists, and actually it's already pre-trained on huge data sets, huge corpus of text, to really specialize in a specific domain like requirements engineering, you would only need a smaller data set, so you can work with the relatively small data sets. And so researchers work quite clever to use this advantage for classifying functional requirements, non-functional requirements, security requirements, and creating various data sets of non-functional requirements. So in one of the studies that we cite, like famous Norbert model got very nice results with 90% of score for functional requirements, 93 for non-functional, and for security requirements, 91% of performance, let's say. So, right. So, yeah, this is some of the results, like related studies. So we are not the first and like far away to be the first to deal with the subject. There is many research in this area, and what we wanted really to contribute to this, to show how exactly this could be used for requirements engineering. And we conducted a series of studies showing how that could be used for requirements extraction. So what we call extraction here is parsing the text, understanding within the text what is the requirement and what is not requirement, right? Also security requirements classifications. Here we talk also about binary classification, saying, okay, we have a set of requirements and let's try to understand what inside is related to cybersecurity, what requirement is related to cybersecurity. And third example that we want to show is some semantic search technology. So we have longer lists of cybersecurity, let's say, recommendations. And when we receive some vague requirement or some requirement that we don't know how to kind of implement, we actually better to look into, let's say, more concrete examples from, for example, security technology implementation guidelines, and to see, I mean, would we find actually specific recommendations, practical, but also checkable and executable. And we are going to show how this could be used. So I have 5 minutes left, I guess, for my presentation. So I will go straightly to implementation. Okay. So how does usually work? Typically, you would have some specific pre-trained models. So we took in this study, we took a model called BERT, by Google, if I'm not mistaken. So it's already pre-trained. So what we only need is to collect specific data set of requirements. That actually, in our case, we had a corpus from the pure data set, and we had actually to parse these documents and get requirement sentences. That with these sentences, we pre-trained or fine-tuned this BERT. And when we receive a document, we parse it, we extract sentences, and then those sentences we give it to BERT, pre-trained model, and it classifies it as a requirement or not requirement. And so we are limited only to getting those of requirements, so that requirements analyst can concentrate on working on specific requirement states. We have taken quite a nice results with that, with a very high precision, with the F1 score about 86%. So we collected a specific data set for that, so which is could be used for those who are interested. And so, in addition, what should be noted that even though we have lower result than the previous authors, we actually did specific effort to test our results in with cross-domain validation. So we tested our results on the document the model haven't seen before to check if we can generalize results and can these models could be practically used in industrial cases. Right. The similar approach could be used for classifying what is security, what is not security, and we have actually combined that requirements classification model with specific second stage when we train the model to understand what is security and what is not, to obtain a list of candidate requirements for the security domain. And it actually works as quite a similar way. We have a list of requirements that we data set that we labeled, we kind of read it and labeled with security requirement or not security requirement. And with that, we obtain the model that should be practical. To give you an example whether it works or not, so just remember our document, right, with software requirement specification that gives us if I were functionalist, analyst, I would definitely first go and see those chapter. But is it everything that is security related in this chapter? And for that, we can run our model. And basically, if I look at this document with our model, we can actually look into. They actually can find specific additional requirements that could be addressed. So, for example, the same documents would say that client-side component of software system must operate within common web browser environment using SSL, the specific cryptographic protocol, which is, I think, very much relevant if I'm the developer and needed to implement the system. So I definitely should actually look at that particular requirement. Also, there are some requirements on roles, super roles, admin roles, which is also quite important and maybe quite linked to cybersecurity aspect and the privacy and protecting information. And privilege escalation, let's say, scenarios. Right. So yeah, this works and it gives some nice results, and so typically we will suggest using that. Another example is semantic search, and here also these NLP methods can help us to, let's say, to compare semantic meaning of various requirements, whether a sentence belongs semantically close to something else. And we particularly use that in trying having a database of STIG recommendations, security technology implementation guidelines. And for the given security requirements, we can actually check what is related to the security requirement to understand whether we can find any particular recommendations for that. And for that was sentences like databases, like requirements from stick database, but the requirements that we actually want to find recommendation for are vectorized, and we look at cosinus similarity so that we can find something relevant. To give you an example, let's take, for example, this SSL security password. Yes, any page securing password, let's say. If I go and stick viewer database and try to find something about securing password, securing wireless access, let's say, what to do for that, and try to find anything, I might find some of those things here. If I look into like Windows, let's say group, it actually looks in the keywords and find out, let's say, based on keywords, what how like wireless access could be secured. If I look in our semantic search algorithm, I can specify actually which platform I want to deal with, like for example, we want to, and sorry, in recommendation, okay. So we actually can, let's say, look at various access, not only from like based on keywords, but also meaning, like here, remote access, and let's say we have remote access, which is not kind of, there is no keywords related to wireless access, but it still relates to this one. And semantic meaning is quite closer to what we need. And based on the semantic let's say, closeness, we can actually obtain the right recommendations with the concrete examples of what, how that could be actually secured. Right. With that, I wanted to stop this presentation. So we had presented few examples on how NLP methods and machine learning-based NLP methods can be used in requirements analysis, specifically for cybersecurity, in some cybersecurity context. So we're currently evaluating our results with industrial studies with our partners ABB and Tagore. We noticed that there might be some high resource demand of this method because this NLP methods are quite huge. So also we face the challenge on how to, let's say, evaluate relevance of semantic search technology, and we do specific development on integrating these technologies as a kind of part of the pipelines that it actually will be covered in our further research. Right.